Einstein's general theory of relativity. A late-night lecture? Good evening. Tonight we will be covering Einstein's general theory of relativity. We will proceed slowly, methodically, and with considerable attention to detail as the subject demands. There is no need to rush. The material will unfold at its own pace, and we will revisit each concept as many times as is necessary to ensure a thorough and complete understanding of what is, admittedly, one of the most mathematically dense and conceptually rich theories in the history of human scientific inquiry. Please settle in. There's quite a lot to cover, and we will cover all of it carefully without omission. Section 1. Historical background and motivation. To understand why Einstein developed the general theory of relativity, we must first understand the state of physics at the close of the 19th century and the opening decades of the 20th. It is important to understand this historical context. The context matters because it explains the problems that needed solving, and it is only by understanding the problems that we can truly appreciate why the solutions took the form that they did. Isaac Newton, writing in his Philosophia Naturalis Principia Mathematica in 1687, had formulated a theory of universal gravitation that was, by any measure, extraordinarily successful. Newton proposed that every massive body in the universe exerts an attractive force upon every other massive body, and that this force is proportional to the product of the two masses and inversely proportional to the square of the distance separating them. In verbal notation, this is: the force F equals the gravitational constant G times the quantity m1 times m2 divided by the quantity r squared. This is Newton's law of universal gravitation. This law, this single equation, was able to account for the motion of the planets, the behavior of falling objects on Earth, the trajectory of comets, the oscillations of tides, and a great many other phenomena. And yet, Newton himself was deeply troubled by his own theory. He was troubled by it for a reason that is worth dwelling upon, because it is precisely this reason that eventually led to Einstein's reformulation. Newton's theory required what we might call action at a distance. In Newton's framework, two bodies separated by an arbitrarily large distance could exert a gravitational force on one another instantaneously, without any intervening medium, without any delay, without any mechanism by which the force was transmitted. Newton himself wrote in a letter to Richard Bentley in 1693 that the notion that one body could act upon another at a distance through a vacuum without the mediation of anything else was to him so great an absurdity that he believed no man who had in philosophical matters a competent faculty of thinking could ever fall into it. Newton said this, and yet his own theory required it. He was aware of the problem. He acknowledged it. He simply did not have a solution. For over 2 centuries, this problem was essentially set aside because the theory worked so extraordinarily well in practical terms that there was little urgency to resolve the philosophical difficulty. It was only with the advent of James Clerk Maxwell's theory of electromagnetism in the 1860s that the inconsistency became truly acute. Maxwell showed that electromagnetic phenomena propagate at a finite speed, the speed of light, which we denote as c, through a field that pervades all of space. If electromagnetism propagated at a finite speed through a field, why should gravitation be any different? There was a growing sense that Newton's instantaneous action at a distance was not merely philosophically unsatisfying, but physically incorrect. Albert Einstein, born in Ulm, Germany, on the 14th of March, 1879, had already, by 1905, produced what we now call the special theory of relativity. This earlier theory is foundational. The special theory of relativity established that the speed of light is the same for all observers, moving at constant velocities relative to one another, that space and time are not absolute and separate quantities, but are woven together into a unified 4-dimensional continuum called space-time, and that no information or causal influence can travel faster than the speed of light. This last point was directly in conflict with Newton's instantaneous gravitational action at a distance The special theory of relativity, in other words, made it essentially mandatory to construct a new theory of gravity. Newton's theory had to be replaced, but the special theory of relativity had a limitation, and Einstein was fully aware of it. It applied only to observers moving at constant velocities, that is, observers in what we call inertial reference frames. It said nothing, at least not directly, about observers who are accelerating. And gravity, as we experience it, involves acceleration. When you drop an object and it falls, it is accelerating downward. Einstein knew that a truly general theory, one that could handle acceleration and therefore gravity, would need to go beyond the special theory. He spent approximately 10 years, from roughly 1905 to 1915, developing this more general framework. The effort was immense, the mathematics was new, and the conceptual leaps required were extraordinary. The general theory of relativity was published in its complete form in November of 1915. To notice this, Section 2, the equivalence principle. The conceptual cornerstone of general relativity is something that Einstein called the equivalence principle. The equivalence principle is the starting point. It is where everything begins. Without the equivalence principle, there is no general theory of relativity, as Einstein formulated it. The equivalence principle, in its simplest statement, asserts that there is no local experiment that can distinguish between the experience of being in a gravitational field and the experience of being in an accelerating reference frame. Let us unpack this statement because it is worth unpacking carefully. Imagine, if you will, that you are inside a closed box. A box with no windows, no instruments that can detect the outside world, nothing that gives you any external reference. If this box is sitting stationary on the surface of the Earth, you will feel a force pressing you toward the floor. You will feel what we commonly call your weight. Now imagine that this same box is out in empty space, far from any gravitating body, and is being accelerated upward at a rate of 9.8 meters per second squared, which is of course the gravitational acceleration at Earth's surface, denoted by the letter g. Inside this accelerating box, you will also feel a force pressing you toward the floor of the box. The force will feel identical. You will feel your weight. There is, Einstein claimed, no local measurement you can make, no experiment you can perform while inside the box that will tell you which situation you are in. The two situations are physically equivalent locally for all local experiments. This is one version of the equivalence principle, sometimes called the weak equivalence principle or the Einstein equivalence principle. There is also what is sometimes called the strong equivalence principle, which asserts that all of the laws of physics, not just mechanical laws, but all of them, including electromagnetism, take the same form in a local inertial frame, regardless of where that frame is located in space-time or how strong the local gravitational field is. The strong form is a more powerful statement. It underpins the entire mathematical structure of general relativity. Einstein arrived at this principle through what he later described as the happiest thought of his life, which he had in 1907. He imagined a person falling freely under gravity, a person in free fall, and realized that such a person would not feel their own weight. A person falling freely feels weightless. We see this today when astronauts aboard the International Space Station float around their cabin. They are in a state of free fall. They are continuously falling toward the Earth, but moving horizontally fast enough that they miss it, and they feel no gravitational force. Their environment is locally equivalent to empty space, far from any gravitating body. The gravitational field is, in some sense, being cancelled by the acceleration of free fall. The gravitational field is being transformed away, locally, by choosing the right reference frame. This was a profound insight. It suggested that gravity is not fundamentally a force in the Newtonian sense. It suggested that what we call gravity is an artifact of the coordinate system, that it is a manifestation of the curvature of space-time itself, and that objects moving freely under gravity are simply following the straightest possible paths through a curved space-time. Let us now examine what this means mathematically. Section 3. Special Relativity and Space-Time. A review. Before we can discuss curved space-time, we must briefly review flat space-time, which is the space-time of special relativity. We need this foundation. The foundation is necessary. In special relativity, space-time is a four-dimensional continuum with coordinates x0, x1, x2, and x3, where x0 equals c times t is the time coordinate, and x1, x2, x3 are the spatial coordinates, which we may also write as xyz. The geometry of this spacetime is encoded in the spacetime interval d's squared, which measures the infinitesimal separation between two nearby events. In special relativity, this interval is given by ds squared equals negative c squared times dt squared plus dx squared plus dy squared plus dz squared. We can write this more compactly using the metric tensor of special relativity, which is called the Minkowski metric and is denoted by the Greek letter eta with two subscript indices, eta, mu, nu. The metric tensor is a 4x4 matrix. In the convention we are using, the Minkowski metric has diagonal entries, -1, +1, +1, +1, with all off-diagonal entries equal to 0. Using this metric tensor, the spacetime interval can be written as ds squared equals eta mu nu times dx mu times dx nu, where we sum over the repeated indices mu and nu using what is called the Einstein summation convention. The Einstein summation convention states that whenever an index appears twice in a term, once as a subscript and once as a superscript, summation over that index from 0 to 3 is implied. This convention is very convenient. It eliminates the need to write explicit summation signs. We will use it throughout this lecture. The Minkowski metric is flat. By flat, we mean that the geometry of spacetime is Euclidean in the spatial directions and pseudo-Euclidean overall. There is no curvature. Parallel lines in Minkowski spacetime remain parallel. The angles of triangles sum to exactly pi radians. The rules of this geometry are, in a certain sense, simple and clean. It is only when we introduce gravity that we must abandon this flatness and work with curved spacetime. Section 4. The Mathematics of Curved Spacetime. The mathematical language required to describe curved spacetime is differential geometry, sometimes called Riemannian geometry, or, for the case of spacetimes with the signature we are using, pseudo-Riemannian geometry. This is the branch of mathematics developed principally by Bernhard Riemann in the 19th century, and it is the branch of mathematics that Einstein had to learn, or more precisely learn from his friend and collaborator Marcel Grossmann in the course of developing general relativity. In a curved spacetime, the metric tensor, now denoted gmu nu rather than eta mu nu, is no longer constant. It can vary from point to point. Different regions of spacetime can have different geometrical properties. The spacetime interval in a curved spacetime is written as ds squared equals g mu nu times d x mu times dx nu, where the metric tensor g mu nu is now a function of the coordinates. This is the fundamental object of general relativity. Everything, the curvature of space-time, the paths of particles, the behavior of light, the dynamics of the universe, can be derived from the metric tensor g mu nu. Now, in flat space, when we take derivatives of tensor quantities, the derivatives of tensors are themselves tensors. But in curved space, ordinary partial derivatives of tensors do not in general transform as tensors. They do not behave properly under coordinate transformations. To remedy this, we introduce the covariant derivative, which is a modified derivative that takes into account the curvature of the space and does transform properly as a tensor. The covariant derivative of a vector v mu, denoted by the nabla symbol or by a semicolon followed by the index, involves the ordinary partial derivative plus correction terms involving what are called the Christoffel symbols. The Christoffel symbols are denoted by the capital Greek letter gamma with one superscript index and two subscript indices. Gamma superscript lambda, subscript mu nu. The Christoffel symbols are given by gamma superscript lambda, subscript mu nu equals 1/2 times g superscript lambda sigma times the quantity partial derivative of g subscript sigma nu with respect to x mu plus partial derivative of g subscript sigma mu with respect to x nu minus partial derivative of g subscript mu nu with respect to x sigma. Here g superscript lambda sigma is the inverse metric tensor which satisfies the relation g superscript lambda sigma times g subscript sigma mu equals the Kronecker delta superscript lambda subscript mu, which is equal to 1 when the indices are equal and 0 when they are not. The Christoffel symbols are not themselves tensors. They do not transform as tensors under coordinate transformations, but they appear in a combination that does behave as a tensor, and this combination is the Riemann curvature tensor. The Riemann curvature tensor is denoted R superscript RHO subscript sigma mu nu, and it is given by R superscript rho subscript sigma mu nu equals partial derivative with respect to x mu of gamma superscript rho subscript nu sigma minus partial derivative with respect to x nu of gamma superscript rho subscript mu sigma plus gamma superscript rho subscript mu lambda times gamma superscript lambda subscript nu sigma minus gamma superscript rho subscript nu lambda times gamma superscript lambda subscript mu sigma. This is a long and somewhat intimidating expression, but it is the correct and complete expression. The Riemann curvature tensor encodes all of the curvature information of the spacetime. If the Riemann curvature tensor is 0 everywhere, the spacetime is flat. If it is non-zero, somewhere the spacetime is curved there. The Riemann curvature tensor is 0 everywhere if and only if the spacetime is flat. The Riemann curvature tensor has 4 indices and is therefore a rank 4 tensor. It has, in 4-dimensional spacetime, 4 to the 4th power equals 256 components. However, owing to various symmetry properties of the tensor, it is antisymmetric in the first pair of indices, antisymmetric in the second pair, and symmetric under exchange of the 2 pairs. The number of independent components is reduced to 20. In a 4-dimensional spacetime, the Riemann curvature tensor has 20 independent components. For the purposes of the field equations, we need objects with fewer indices. We obtain these by a process called contraction. The Ricci tensor, denoted R mu nu, is obtained from the Riemann tensor by contracting the first and third indices. R mu nu equals R superscript lambda subscript mu lambda nu. The Ricci tensor is a rank 2 symmetric tensor. It has 10 independent components in 4-dimensional spacetime. Further contracting the Ricci tensor with the inverse metric tensor gives the Ricci scalar, also called the scalar curvature, denoted simply R. R equals G superscript mu nu times R mu nu. The Ricci scalar is a single number at each point in spacetime, and it provides a single overall measure of the curvature at that point. From the Ricci tensor and the Ricci scalar, we construct the Einstein tensor, denoted G mu nu. G mu nu equals R mu nu minus 1/2 times G E mu nu times R. The Einstein tensor is also a rank 2 symmetric tensor. It has 10 independent components, and it has a very important property, which we shall state without full derivation, but which follows from a result known as the contracted Bianchi identities. The covariant divergence of the Einstein tensor is 0. That is, the covariant derivative of G mu nu with respect to the index nu is equal to 0. Written with index notation, G superscript mu nu semicolon nu equals 0. This is a profound property. It is, in some sense, a geometric identity. It holds automatically, regardless of any physical content, simply because of the way the Einstein tensor is constructed. and it will have important consequences for the conservation of energy and momentum. Section 5. The energy-momentum tensor. On the right-hand side of Einstein's field equations, we need an object that describes the matter and energy content of the spacetime. This object is called the stress-energy tensor, or the energy-momentum tensor, denoted T mu nu. The energy-momentum tensor is also a rank 2 symmetric tensor with 10 independent components. Let us describe verbally and carefully what each component of this tensor represents. The component T00 represents the energy density, the amount of energy per unit volume of the matter or field at a given point in space-time. The components T0I, where I takes the values 1, 2, or 3, represent the momentum density in the ith spatial direction, the amount of momentum per unit volume flowing in that direction, by the symmetry of the tensor Ti0 equals T0I, and represents the energy flux in the ith direction, the rate at which energy flows across a surface perpendicular to the ithe direction. The components Tij, where both I and j are spatial indices, represent the stress tensor. Specifically, Tij represents the flux of the ith component of momentum in the jth direction, which is equivalent to the force per unit area, that is the pressure and shear stress, exerted across a surface perpendicular to the jth direction. For the simplest physical case, that of a perfect fluid, a fluid with no viscosity and no heat conduction, the energy-momentum tensor takes a particularly simple form. In the rest frame of the fluid, the energy-momentum tensor of a perfect fluid is T mu nu equals the quantity rho times c squared plus p times u mu times u nu plus p times g mu nu, where rho is the rest frame energy density, p is the pressure, and u mu is the forward velocity of the fluid. The forward velocity u mu is the derivative of the space-time coordinates with respect to the proper time tau. U mu equals dx mu divided by d tau. The covariant divergence of the energy-momentum tensor is, by the principle of energy and momentum conservation, equal to 0, that is, t superscript mu nu semicolon nu equals 0. This is the mathematical expression of the local conservation of energy and momentum. The local conservation of energy and momentum. We say local because general relativity does not in general admit a straightforward global conservation law for energy, but locally, at each point in space-time, energy and momentum are conserved in the appropriate sense. Section 6. Einstein's field equations. We now have the ingredients necessary to state Einstein's field equations. These are the central equations of general relativity. They are the equations that Einstein arrived at in November of 1915 after years of struggle and several false starts. They are, by common consensus, among the most beautiful and consequential equations in the history of physics. Einstein's field equations state that the Einstein tensor is proportional to the energy-momentum tensor. In symbols, g mu nu equals 8 pi times g divided by c to the 4th power times t mu nu. Let us read this equation slowly and carefully. G mu nu is the Einstein tensor, a quantity derived entirely from the geometry of space-time, encoding the curvature of space-time at each point. T mu nu is the stress-energy tensor, a quantity describing the distribution of matter and energy in space-time. The constant of proportionality, 8 pi times g divided by c to the 4th power, involves the Newtonian gravitational constant g and the speed of light c. This constant of proportionality is sometimes called the Einstein gravitational constant or the coupling constant of general relativity. This equation says, in its essence, that the curvature of space-time, encoded in g mu nu, is determined by the distribution of matter and energy encoded in t mu nu. Matter and energy tell space-time how to curve, and the curved space-time, in turn, tells matter how to move. This last point, curved space-time tells matter how to move, is not explicit in the field equations themselves, but is encoded in a separate statement, the geodesic equation, which we will discuss momentarily. Let us pause to remark on the elegance of the structure. The left-hand side of the Einstein field equations, G mu nu, automatically satisfies the conservation condition. Its covariant divergence is 0. The right-hand side, T mu nu, also satisfies the conservation condition. By physical law, its covariant divergence is 0. The two sides are compatible. The structure is self-consistent. This self-consistency, this compatibility, is not an accident. Einstein specifically constructed the left-hand side to have this property precisely so that it would be compatible with the known conservation of energy and momentum. It is also worth noting that the field equations, written as G mu nu equals 8 pi g over c to the 4th power times T mu nu, actually represent not one equation but 10 equations, one for each independent component of the symmetric rank 2 tensors on both sides. 10 equations, and they are not 10 independent algebraic equations, because the contracted Bianchi identities impose 4 constraints on them, reducing the number of truly independent equations to 6. These 6 equations, together with appropriate boundary conditions and gauge conditions, determine the 10 components of the metric tensor G mu nu. Einstein also later introduced and then retracted and then found, rehabilitated by cosmological discoveries, an additional term called the cosmological constant. The field equations with the cosmological constant are G mu nu plus lambda times G mu nu equals 8p g over c to the 4th power times T mu nu, where lambda is the cosmological constant. Einstein introduced this term in 1917 in order to produce a static cosmological solution. He believed, as most people of his era believed, that the universe was static and neither expanding nor contracting. When Edwin Hubble and others showed observationally in the late 1920s and 1930s that the universe is in fact expanding, Einstein reportedly called the cosmological constant his greatest blunder. And yet, since the 1990s, astronomical observations have shown that the expansion of the universe is accelerating, and the cosmological constant, or something functionally equivalent to it, appears to be necessary to explain this acceleration. It is now interpreted as a form of energy inherent to the vacuum of space, sometimes called dark energy. Domos in Nadone. Section 7. Geodesics and the motion of particles. We said that curved space-time tells matter how to move. Let us now describe precisely how it does so. In general relativity, freely falling particles subject to no non-gravitational forces, move along what are called geodesics of the curved space-time. A geodesic is the generalization of a straight line to curved space. In flat space-time, geodesics are straight lines in both space and time, corresponding to uniform motion at constant velocity. In curved space-time, geodesics are curved paths, and these curved paths, when projected onto three-dimensional space, look like the curved trajectories we observe for objects moving under the influence of gravity. The geodesic equation, which describes the motion of a freely falling particle, is the second derivative of x mu with respect to the proper time tau plus gamma superscript mu subscript nu lambda times the first derivative of x nu with respect to tau times the first derivative of x lambda with respect to tau equals 0. Written more compactly, d squared x mu over d tau squared plus gamma superscript mu subscript nu lambda times dx nu over d tau times dx lambda over d tau equals 0. This is the geodesic equation. Let us interpret it. The first term, d squared x mu over d tau squared, is the coordinate acceleration of the particle, how rapidly the coordinate velocity is changing with proper time. In flat space-time with no curvature, the Christoffel symbols are all 0, and the geodesic equation reduces to d squared x mu over d tau squared equals 0, which says the coordinate acceleration is 0. The particle moves in a straight line at constant velocity. In curved space-time, the Christoffel symbols are not 0, and they produce an additional term that, in the Newtonian limit, reproduces the gravitational acceleration predicted by Newton's law of universal gravitation. This is one of the ways in which general relativity reduces to Newtonian gravity in the appropriate limit, the limit of slow velocities and weak gravitational fields. Light also follows geodesics in general relativity, but because light has zero rest mass and travels at the speed of light, its world line is null, meaning the space-time interval d squared along its path is zero. For null geodesics, the proper time tau is not a useful parameterization, and one uses instead an affine parameter. The geodesic equation takes the same form, but with the proper time replaced by this affine parameter. The prediction that light follows curved paths in the presence of gravity, a prediction that is a direct consequence of the geodesic equation in curved space-time, was one of the early tests of general relativity, confirmed observationally by Arthur Eddington's famous solar eclipse expedition in 1919. The Durto, Section 8, the Newtonian limit. It is important to verify that Einstein's field equations reduce to Newton's theory in the appropriate limit. This is necessary for the theory to be physically plausible, since Newton's theory is known to be extremely accurate in the regime of weak fields and slow motion. The appropriate limit to take is the gravitational field is weak, so that the metric is only slightly different from the flat Minkowski metric. The field is also static, meaning it does not change with time. And all velocities are much less than the speed of light. In this limit, we can write the metric tensor as g mu nu equals eta mu nu plus h mu nu, where eta mu nu is the Minkowski metric and h mu nu is a small perturbation, with all components of h mu nu much less than 1. We substitute this into Einstein's field equations and keep only the lowest order terms in h mu nu. The result, after considerable algebra, which we will not reproduce in full here, is that the time-time component of the perturbed metric satisfies the Laplacian of h00 equals negative 16 pig over c squared times RHO, where ARHO is the matter density and the Laplacian is the sum of second partial derivatives with respect to the three spatial coordinates. Now, in Newtonian gravity, the gravitational potential phi satisfies Poisson's equation. The Laplacian of phi equals 4 pi g times a rho. Comparing these two equations, we find that h00 equals negative 4 phi over c squared, and the metric component g00 equals eta 00 plus h00 equals negative 1 minus 2 phi over c squared. The geodesic equation in this limit with low velocities reduces to d squared xi over dt squared equals negative the partial derivative of phi with respect to xi. This is precisely Newton's second law of motion in a gravitational potential phi, which in turn satisfies Poisson's equation. The Newtonian limit is correctly reproduced. Einstein's theory contains Newton's theory as a special case, valid in the limit of weak fields and slow motion. Section 9. Solutions to Einstein's field equations. Einstein's field equations are a system of 10 coupled, nonlinear, partial differential equations in the components of the metric tensor. In full generality, they are extraordinarily difficult to solve. Finding exact solutions in closed form, requires imposing symmetry conditions to reduce the complexity of the problem. The first and most important exact solution was found by Carl Schwarzschild in December of 1915, just weeks after Einstein published the final form of his field equations, and remarkably, while Schwarzschild was serving on the Russian front during the First World War. Schwarzschild found the solution for the space-time geometry exterior to a spherically symmetric, non-rotating, electrically neutral mass. The Schwarzschild solution, as it is now called, gives the metric in the form ds squared equals negative the quantity 1 minus 2 gm over c squared IHEs times c squared dt squared plus the quantity 1 minus 2 gm over c squared AER to the power negative 1 times dr squared plus IR squared times the quantity d theta squared plus sin squared theta times d phi squared Here m is the total mass, r is the radial coordinate, and theta and phi are the angular coordinates. This metric has a very interesting and physically important feature. The coefficient of dt squared goes to 0, and the coefficient of dr squared diverges at the radius or equals 2gm over c squared. This special radius is called the Schwarzschild radius, and it defines what we now call the event horizon of a black hole. At and inside the Schwarzschild radius, the roles of r and t, as spatial and temporal coordinates, are in a certain mathematical sense exchanged, and the inevitable flow of time inside the horizon is directed toward decreasing r, meaning everything inside the horizon inexorably falls toward r equals 0. At r equals 0, the curvature of space-time becomes infinite, a genuine physical singularity, not a coordinate artifact. This is the singularity at the center of a Schwarzschild black hole. The existence of singularities under very general conditions was later proven rigorously by Roger Penrose and Stephen Hawking in what are called the Penrose-Hawking singularity theorems developed during the 1960s. Another important solution is the Kerr solution, found by Roy Kerr in 1963, which describes the space-time geometry around a rotating, uncharged black hole. The Kerr solution is more complex than the Schwarzschild solution, but is astrophysically more relevant, since all real massive objects rotate. The Friedmann-Lemaitre-Robertson-Walker metric, often abbreviated as FLRW, describes a homogeneous and isotropic cosmological space-time, one that looks the same at every point and in every direction, and is the basis of the standard model of cosmology. Section 10. Observational tests and applications. General relativity has been tested with great precision by a variety of observational and experimental means. Each test confirms the theory to remarkable accuracy. Let us review several of these tests methodically. The first test is the precession of the perihelion of Mercury. In Newtonian gravity, the orbit of a planet around the Sun is a closed ellipse. In practice, gravitational perturbations from other planets cause the ellipse to precess. That is, the orientation of the ellipse slowly rotates. By the 19th century, astronomers had measured the total precession of Mercury's perihelion, the point in its orbit closest to the Sun, to be about 5,575 arcseconds per century. Newtonian gravity, accounting for all planetary perturbations, could account for all but 43 arcseconds per century. This discrepancy of 43 arcseconds per century was unexplained within Newtonian gravity and was considered a significant anomaly. General relativity, applied to the orbital mechanics of Mercury, predicts an additional relativistic precession of exactly 43 arcseconds per century. The agreement between theory and observation is essentially exact. This was one of the first confirmations of general relativity. The second test is the deflection of light by the Sun. General relativity predicts that light passing close to a massive body will be deflected by the curvature of space-time. For a light ray grazing the surface of the Sun, the predicted deflection is 1.75 arcseconds. Arthur Eddington led an expedition to observe the positions of stars near the Sun during the total solar eclipse of May 29, 1919. During totality, the Moon blocked the Sun's light, making it possible to photograph stars near the solar limb and compare their apparent positions with their positions when the Sun was not nearby. The observed deflection was consistent with Einstein's prediction, and the results were announced on November 6, 1919, making Einstein instantly famous worldwide. The third test is gravitational redshift. General relativity predicts that light emitted from a region of strong gravitational curvature will be redshifted. Its frequency will be decreased as it climbs out of the gravitational potential well. This is a consequence of the equivalence principle. In 1959, Robert Pound and Glenn Rebka performed a famous experiment at Harvard University, the Pound-Rebka experiment, in which they measured the gravitational redshift of gamma rays over a height difference of 22.5 meters in the Jefferson Laboratory Tower. The result agreed with general relativity's prediction to within about 10%. Subsequent experiments have confirmed the gravitational redshift to far greater precision. The fourth test And one of the most dramatic confirmations in recent years is the detection of gravitational waves. General relativity predicts that accelerating masses will produce ripples in the fabric of space-time, gravitational waves that propagate outward at the speed of light, carrying energy away from the source. These waves cause tiny oscillating distortions in the distances between freely falling objects. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected a gravitational wave signal for the first time. The signal was consistent with the merger of two black holes, each of roughly 30 solar masses, at a distance of approximately 1.3 billion light-years. The peak gravitational wave strain, the fractional change in length of LIGO's 4-kilometer arms, was approximately 1 × 10⁻21. This is an extraordinarily small number. It means the arms changed in length by less than the width of a proton. The detection was a stunning experimental achievement and a profound confirmation of general relativity. The leaders of the LIGO project were awarded the Nobel Prize in Physics in 2017, a fifth application of general relativity, one that has everyday practical significance, is the Global Positioning System, or GPS. The GPS system relies on a network of satellites in medium Earth orbit, each carrying atomic clocks. By measuring the time it takes for signals from multiple satellites to reach a receiver, the receiver can determine its position on Earth. General relativity produces two time dilation effects that must be accounted for. First, gravitational time dilation, which predicts that clocks in the weaker gravitational field of orbit run faster than clocks on the ground, a relativistic effect amounting to approximately 45 microseconds per day. Second, the time dilation of special relativity due to the orbital velocity of the satellites, which causes their clocks to run slower than ground clocks by approximately 7 microseconds per day. The net effect is that GPS satellite clocks run faster than ground clocks by approximately 38 microseconds per day. If this correction were not applied, GPS position errors would accumulate at a rate of roughly 11 kilometers per day, rendering the system useless for precise navigation. The practical utility of general relativity in everyday technology is therefore well established. Kurasint, Section 11. Cosmological implications. We have already mentioned the Friedmann-Lemaitre-Robertson-Walker metric as a solution to Einstein's field equations, applicable to a homogeneous and isotropic universe. Let us describe briefly the cosmological content of this solution. The FLRW metric describes a universe that is the same at every point in space, homogeneous, and the same in every direction, isotropic. The metric is written as ds squared equals negative c squared dt squared plus a of t squared times the quantity dr squared divided by 1 minus kr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Here, a of t is called the scale factor. It is a function of time that describes how the overall size of the universe changes with time. The constant k is the curvature parameter, which takes the value +1 for a positively curved closed universe, 0 for a flat universe, and -1 for a negatively curved open universe.